recording it. Good. So this octave exercise is about the responses. So responses, we had the impulse response, step response, frequency response, and then from the frequency response, you can calculate amplitude or magnitude response and phase response. Phase response also have the one important part is the group delay, especially when this frequency dispersion is a critical factor on a system, or if you want to compensate for frequency dispersion. Okay, so responses. On the exercise, I have actually this, you will again determine the system parameters of A and B for the following system. I will definitely go through this exercise 2 returns on Monday at latest, since that's where the most of the mistakes will happen. And if you do the same mistake also in here, then you have lost a couple of points already. But anyways, let's take a little bit different approach. So I will also show you how to make this, say, system from a zero pole diagram. So in this exercise, you will start from transfer function, then basically analyze the step, the impulse response, then the frequency response, plot zeros and poles, group delay, scale the system, and then use the system with a analog signal. Okay, in this, I will show you also a little bit different approach. So basically, the transfer function has these two forms. From difference equation, you can easily take and calculate this this sum form of transfer function, which is, let me go a little bit back. Okay, somewhere in here I have this transfer function. Okay, so it has this the sum form where the polynomials are shown as the weighted sum of, and then okay, that doesn't actually really show that in here. Maybe I should open the systems block diagram, transfer function. Okay, transfer function. Okay, here we have. So transfer function has the sum form where the polynomials are actually the sum form polynomials, or then the broken into first order polynomials and a product of those first order polynomials. Both of these forms are exactly the same. Really, but let's take a look at a design by heart, so to speak. I will start designing by setting the zeros and poles for the system. Example. From the zero pole plot. For example, let's put a sampling rate so that we have a real system. So that's 1000 Hertz sampling rate. And then we have a noise frequency at 50 Hertz. Well, sometimes we do. Well, usually it's at 100 Hertz. Well, let's put it on 100 Hertz in it, just for fun. 100 Hertz a sampling rate. No, this is noise frequency. Noise from a bad AC DC power supply, linear power supply. You decided to design the power supply by yourself or took the cheapest one you can find from eBay. Okay. Or Alibaba or some other network shop. It just have the input and output and a white box. Guaranteed to give you some noise. Okay, that would be a problem unless we can actually try to reduce this line humming by, okay, putting a pole pair at unit circle at circle at omega equals 100. Oh, actually it's 2 times pi times 100 divided by 1000. That's the angle. And well, while we are at it, why not to just make it like this? Okay, here we have the omega for, not pole pair, it's a zero pair. Sorry about that one. A pole will be used to adjust the gain. Okay, so pole. Oh, that was 0. And now the 0 itself must actually have this one, J times omega, but also the complex conjugate pair. And how to tell MATLAB or Octave that this is a zero or pole, you actually put J and minus J. So that will be the complex conjugate pair, but you actually produce a row vector. Oh, sorry, column vector. So 2 components, 2 by 1 vector. It means that yes, 2 special places. It's the 0.80902 plus that. So that's the coordinate, and we can plot it by using z-plane function. Let's just put it ZZ here. Let's see what happens. Does it do anything? Yes. Okay. So that's where the this angle omega is for suppressing that 100 hertz line noise. If you need more suppression, then you can actually, or also other frequencies, for example, 200 hertz, yeah, it can be done. 400 hertz, yes, can be done. 600 hertz, well, it is the same as 400 hertz. Remember that this top half and bottom half on this complex plane, they're always symmetrical. Okay, mirror symmetry. Good, so those are the zeros. And now if we then know that, okay, our actual signal is, could be DC. So if I calculate the transfer function from that one and just put the poles at origin. So this would be FIR system. FIR system when the poles are at 0, second order system. But now I have the polynomials, meaning that, okay, I have actually, I know these coordinates. the polynomial form of this the system, and I can actually turn this one into system coefficients B and A by simply saying BB equals the polynomial defined by roots Z. There. And it really doesn't matter what the values are here, but it's 1 minus 1.618 more 1, and then AA is the polynomial, second order polynomial, which has roots at the same as poles. All right, and here we have 1, 0, 0, which means basically that our y of n equals x of n minus 1.618 times x of n minus 1 plus x n minus 2. Then, well, that's it. It doesn't have feedback based on this one, because the polynomial is just 1, 0, 0, meaning the terms for the feedback term are turned off for the y. And this 1 is actually multiplier for the yn. Okay, so that's the difference equation. How to implement this one? Well, the implementation is called filter. But anyways, so that's one system, and now I can calculate the frequency response for this system. BB, AA. Okay, now I don't remember everything, so help on frequency response, BAN sampling rate. Okay, let me calculate the frequency response. It's simply you type the system coefficients, first the X coefficients, which are called B. That's the usual way. If you just happen to rename those B and A separate, you know, swap those there. Remember to swap those everywhere. So it's better not to swap anything. Just use the convention that is, well, history convention from year 0 or something like that, where the input, these scaling factors are B and the output scaling factors are A. Then I want to calculate this one at, for example, 124 points and give it the sampling rate. System coefs BA number of points where to evaluate this one, and then sampling rate. And I have the figure somewhere. Okay, yeah, it's nice. It suppresses that 100 Hertz, but it's not low pass filter. If our information was here, I would say this is a problem. It's not, it's actually high pass filter. We also want to suppress this one. I could add more zeros here. That's one way, but the calculation become more and more intense. What I can actually do, I can move the pole a little bit of the 0, for example, at poles closer to unit circle, so that I can get more gain at near 0 frequency. I try also something fancy here and try to get almost flat passband, but sometimes it works, sometimes it doesn't. Okay, so for that one, I will take a say 20 hertz at angle 20 hertz frequency. There. So my pole will be some radius. Or actually, I will just first calculate this one. Omega 20 equals 2 times pi times 20 divided by sampling rate. Okay, that's the corresponding angular frequency. And then I will just eyeball it something like this and put the poles at radius of 0.9. This is just a guess. We can tweak this later, but actually this is not usual way of designing filters in any ways, but it can be done this way too. And then we have J minus J against complex conjugate pair times omega 20. So now I have pole bear at, let me put that one in new figure, at near origin. Yes. So as you can see, this actually puts some gain near near the low frequency here, because if you have either j omega here nearby, then the distance to this is very close, so you get about, well, about a magnitude of 10 and the 10 times amplification, or more than 10 times, about 50 times more amplification. Since this is about 0.1 in this point, or maybe I should actually make it a little bit bigger, since in case you have smaller screen. So the distance here is 0.1. This seems to be about 0.2. So on denominator, we now have a gain of 10 and 5. So it's 50 times gain on that region. So we supposed to get quite a lot of dBs at amplification on the near this DC, and corresponding system coefficients. The BB coefficients are still the same, but now we basically changed that one. The poles moved, and now we have AA on. Okay, let me print those. Okay, these are non-zero terms, so basically, do I have it? Corresponding the difference equation, see the sign. So the first term is for y of n, then the second term is minus y of n minus 1, and the third one is also minus n minus 2. There we go. So that's the corresponding difference equation. And this, let me close that one, and then we calculate the frequency response. But let me put that one on different window again. Wow. Okay, so we have fairly flat passband. We have infinite attenuation at 100 hertz, and the stop band attenuation is about 20-25 dB in here, 26 dB actually. So 26 dB stop band attenuation. The only small problem is that this is not unity gain system anymore. So it's not a unity gain, so meaning the highest, the amplification is 1. We can scale it. Brute force approach. Let's calculate the current gain. Maximum gain. So maximum of absolute value of, okay, so we have frequency response. I don't care how many points, or the at what is the frequency here. I just want to know these values here. Magnitude response. This actually returns the frequency response, complex numbers, and absolute value of the frequency response is the amplitude response or magnitude response, and maximum of that one is the maximum gain. Oh, okay, 15.879. Yeah, so it's not 50, but yes, in a sense, it's 50 times larger than without. So remember, it had quite a lot of suppression due to this proximity of 0 point already in this region, the original. So compared to that one, this one is 50 times bigger. And now we can simply say BB equals BB divided by GG. So this is how you're scaling for unity gain. You calculate the maximum gain, divide the BB values with this maximum gain, and then we have frequency response. Whoa, I put it on the wrong graph. Okay. Doesn't matter. So now we have a unity gain filter suppressing the 100 hertz line humming and stop band attenuation around 26 dB, around 25, 26 dB. Okay, so this is how you do a system starting from some parameters like, okay, sampling rate known. We have done some the frequency analysis and noticed, okay, there's noise from a bad power supply, 100 hertz. And then we set the circle at unit circle, yeah, putting a 0 pair at unit circle, not pole pair, and then calculating the omega corresponding fractional frequency, and putting again, this is the complex conjugate pair. Why complex conjugate pair? Well, otherwise, think of this product form compared to this sum form, how to get real values for system coefficients. You must actually have the special points either as complex conjugate pairs, or if you have a single, then it must be on the unit on this real axis. same way as in analog systems, complex conjugate pairs. Okay, and then from these zeros you can calculate the polynomial coefficients, and then originally we have had this finite impulse response where it started, put the poles at the zero. It must have poles, otherwise it's not a system, it just has the input, not output. Okay, and then calculating the frequency response, adjusting the gain by putting these poles on different place, closer to the DC component, adding some gain on the DC components, on the low frequency components, still having this one 0 at 100 Hertz, and then finally calculating the max gain of the system to normalize it. Okay, so those were the frequency response, and then it also had the zeros and poles. And we practically, there's only one thing to do on this in here, how to calculate the group delay. Now I need to remember. Was it group delay? Yes, it's group delays, GRB delay. Ah, wow. I can actually calculate the group delay just like that, and that it has to be a number of points and sampling rate. That's nice. So we have these parameters, system coefficients, B and A, which are system coefficients for the difference equation, exactly the same in transfer function. You can use those to actually calculate the frequency response. You can directly call z-plane with those parameters to check where the zeros and poles are, and for group delay. So if I just say new figure, group delay, B, A, 1024 points. Well, use your own number if you want to, but this works fine. In principle, you want to have more than few hundred points so that this graph looks nice and smooth. You need more points than you have pixels horizontally, and that just happens to be power of 2, so I like that kind of numbers. So the group delay, whoa, doesn't work as I thought. Sorry about that. So it actually does not, yeah, it also returns the values. So, but the group delay looks like that. Sorry about the messing my command window. The command history works just fine. So if you want to look at what I have been writing here, they are right here. This time I hope that nothing actually. Let me do something here just for fun. Last time I lost the history. There. I'm not going to lose it again. So, group delay. This is in number of points. It does not directly calculate it as a number, as the time. But no, sorry. Yeah, this is this upper scale is actually how many samples is the delay. We had one kilohertz sampling rate. So this is now in milliseconds, the group delay in milliseconds. Maybe I should actually mark it here. In samples. Y label, X label. That's the frequency. And in hertz, a Z0 is. Okay, so we can see that on passband we have 8 to around 11 samples time delay. So 8 to 11 millisecond time delay for different frequency component on that range. So when we added a non-zero pole, making it IIR system, all IIR systems have a non-linear phase response. However, you now need to ask yourself, does it really matter? So if it's a application where the pulse form must be reserved, meaning frequencies, different frequency components on passband must actually delay the same amount of time on the system, then you must also use finite impulse response system. But in this case, I didn't care. So now I have some group delay. See the zoom. So the group delay changes. So the changes by the frequency. So at around, let's see, our passband in here, where is the minus 3 dB point? Around about 25 hertz. So around 25 hertz. So practically we are talking about that range. So the time delay varies depending on the frequency between 8 and 11 milliseconds. So this is a dispersion of 3 milliseconds for this signal frequency ranges. Oops. Okay, so that's what the group delay looks like. And this is what the frequency response looks like. Then we had somewhere the zero pole plot. Okay. Let's take a look at what's next. So, frequency, zero pole, plot the system, group delay, scale the system, unity gain. Good. That's the frequency axis stuff, or frequency space. Let's move on the time space and calculate what is the impulse response, which is simply h of n equals system response for delta. And let me take again the region of interest, for example, from -3 to 15, arbitrary numbers. Usually you don't need more than 20 points. 20 points is enough to produce a nicely looking picture. So graphics, if you do graphics, they must contain the information, but then also look nice. That's a general idea. So that's the region of interest. And then we make the delta function is double, same way as last time, n equals to 0, delta. So that's a discrete delta. And the system response is filter system coefficients b and a for data d. So I don't remember if I already had this, but filter actually is the system implementation in MATLAB or Octave. Okay, now I have calculated the impulse response. New figure, I can stem plot it, NNHH. Wow, looks like that. Looks interesting, especially the first point here. There's impulse and then it has this kind of decay. Or actually slow attack and then decay. But well, I was kind of expecting something like that. So practically speaking, it's a maybe I need more points. It didn't look great yet. It just looked good, but not great. Where did I put my here? And HH to see how it actually decays. Wow, okay, that's interesting. So it goes like that and overshoots and then undershoots. FIR or IIR? Definitely IIR. First of all, well, the poles are not at 0 anymore. That also it already tells me. But actual proof will be here. This is the impulse response of second order system. Second order system. So basically the maximum delay of data on that system is 2. So maximum delay, or actually it's minimum delay. Minimum delay is 2. If there's anything after the minimum delay or the highest order delay, if there's anything here non-zero, then it's an IIR system. So definitely IIR system. So most definitely. There we go. So I have a bad feeling about this. Yeah. So now we have more or less analyzed the system on frequency and time-based. So on time-based, most important is the, well, this the impulse response. We could actually also calculate the step response. Okay, while we are here. So step function is simply double n is greater than equal to 0. And then h8 is not hh anymore, but usually step function is s, marked as s, filter, bb, aa, uu. And new figure. So the step response of the system looks like that. You may have heard about final value theorem. You will actually next time. That will be about control. Final value theorem is quite important there. So basically, final value theorem just tells that, okay, if the step response converges into some the constant value, then the system is stable. Okay, but step response right here. So now we started from zero pole plane. Oops. Figure Z-plane, zeros and poles. Started adjusting the poles on the right place. First, we've selected the 0 at 100 Hertz, then adjusted the passband gain, calculated the corresponding the parameters, got the frequency response, calculated the maximum gain and scaled the system. Then calculate group delay to see, okay, actually there is a from 8 to 11 milliseconds since the sampling is 1000 Hertz. So 1 millisecond samples. So 8 to 11 milliseconds of delay variance on passband. Calculated the impulse response and also calculated the step response. Did I close it already? Probably. Okay, let me close these. Since next we will do some spectral stuff. So some spectrum analysis. Last time I think there was the spectrogram. Was it spectrogram on the last exercise? No, it's here actually. Okay. So spectrum analysis. That basically we've covered that theory on the last week. I don't remember what the exercise though. Well, anyways, let's do it here. So spectrum analysis is actually quite simple since the power spectrum of signal is simply Fourier transform of signal times the complex conjugate of signal. Okay. So that's how you calculate a spectrum. But there are some, say, features due to the way we are calculating. Oh, not like that. FFT, of course. The fast Fourier transformation. That comes from the algorithm. But anyways, let's think that we have this. Let's simulate a little bit. So we have sampling time is 1 over fs. And we have a sinusoid signal. So xx is 0.2 times sine of 2 times pi times 100 Hertz times, sorry. I make the time vector to make this one, sample time vector to make this one actually 1 second long. So there is about 1000 samples in here. 1000 samples, 1001 samples at that sampling rate. And now we can generate a signal, test signal. For example, 0.2 is the amplitude times sine of 2 times pi times, let's make it 100 Hertz times TT. Okay, plus 0.1 times random numbers, same size as time. This is the test signal. Noise Cannot sound it since it's 1000 hertz. The Sound Blaster doesn't quite like it. But anyways, it would be a typical uh, um, measurement. If I plot it, it looks like that. And basically, you can see that maybe there is some frequency component there, but it's also lots of noise on it. Now we are trying to, or it could be just the 100 hertz could be also that noise we want to get rid of. Okay, as we did on the previous filter. So that's our data. We don't know yet what it is all about. We can calculate the power spectrum. This is complex power spectrum. We calculate the FFT. Okay, not yet. I will calculate this one so that it's actually calculating the first 512 values. FFT actually likes 2 to the power of n samples. You can actually calculate also for the whole set. It makes not much difference, except that it'll take 1 millisecond for the whole thing, but for Fourier transformation method, we'll do it in few, tens of microseconds. So it does not make any difference in this case. Okay, but anyways, FFT likes 2 to the power of n samples. And this is how you take the first 512 of those. And now we can calculate a power spectrum for that set XXS. So FFT of XXS dot times complex conjugate of FFT of XXS. There we go. So that's the power. And we can either plot this one, but if we are plotting, actually I need to do some fixing of the frequency scale. We calculated the Fourier spectrum in 512 points, meaning that we actually have to have as many frequency points. It starts from 0, which means that, well, you can do it like this. So 1 to 512 minus 1. That's actually 0 to 511. Then basically we scale this one to between 1 and 0 and 1. So now it's normalized between 0 and 1, where 1 means same as the sampling rate. So let's take a look at some theory part here where we have the frequency response. Okay, when we start the frequencies from 0, we go to here. This is sampling rate or 2. Then we have the negative frequencies and actually, well, or positive frequencies which are higher than pi angle. So this point here is 0, 2 pi, 4 pi, 6 pi, and so on. So that's how you scale the frequency axis. Okay, let's take that back actually. We need to plot only this half of the data, because this is just the mirror image. So for plotting, we need only half of the spectrum. spectrum. So we take FNN, like the frequency indexes from 1 to 250, 7 to be actually correct. 256 would be one short. So 257th is actually the sampling rate over 2 because it started from 0. Okay, there. And now we can plot. Of course, I shouldn't plot since, well, FF at FNN and also PX at FFN. Of course, this should be a, where did it go? Error. Oh, FFN. FNN. There we go. Ha! Totally wrong. This is power. And I plotted it in linear scale. No, we need to do the decibels. 10 times log of 10 of px dB. So wherever, oops, dB, in dB, of course. Okay, I have no idea where that display all 2081 possibilities. I pressed some control button here. But anyways, now I can plot. As this digital domain, the spectral plots usually are, we have linear frequency scale compared to the analog systems. Usually you have the logarithmic scale. In these, for the historical reasons, it's a linear scale, the frequency axis. But anyways, now we have the power in decibels. Okay, power in decibels. There we go. So at 100 Hertz, we have this peak and then with flat spectrum. Okay, so that is one frequency plot. Another frequency plot is the spectrogram. And did we already have the spectrogram? I have a feeling that we did, but oh boy, same head, day and night. Assignments, DSP systems, template. No, we didn't have. Okay, spectrogram. It was just the theory last time. Spectrogram, we have a function called spectrogram. If you are using MATLAB, then it has the function name is spectrogram. And you use it something like that. So spectrogram, data, how many points, and then sampling rate. And the spectrogram actually calculates lots of these spectra and puts those in color scale. I'm not sure how well it actually looks like when we have this a limited number of points. Our data is X. Wait a minute, what is the N here? Default segment. Okay, how many points in each segment of data? N, oops, something small. We had only 1000 points. Something small, power of 2, maybe 64. Then next one was the sampling rate. Then we can actually also mark here the overlap. I will mark there. Usually the overlap is, or was it the window and then overlap? Yes. Window is the same as this number of points unless window means how wide window we are using. So we can artificially actually add here zeros to get more spectral resolution. Since this mapping is always done linearly to how many points this the whole range was divided. So basically you just divide the sampling rate by the number of points in the window that defines what is the frequency resolution of this picture. And speaking of picture, okay, it looks like that. It's not that awful when you don't expand it too much. So it shows how the power of this signal power spectrum varies by time. And there is that one signal which is constant, which usually means it's noise, but it's at 100 hertz. And we have a filter. Okay, let's filter and see what happens to that noise. So apply the filter. So output of the system, which is defined by B and A, and input is X, is like that. Okay, and then figure, and let's see what happened to that noise. Wow. So frequency scale here. Okay, this shows that we don't have that high frequency noise here anymore. So it's actually dark, which means low values. And we have more power on small frequencies, meaning DC frequencies, than higher frequencies. On the other hand, we can also calculate the now let me do this one brute force. Okay, the YY points 1 to 512. Calculate the power spectrum for Y, dB, dB, Y, and then new figure and plot F, oops, F, 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 N, and dB, by F, N. And if everything goes well, I get the, yes, I got the power spectrum of this signal when it's, okay, this is where we started. That's the original spectrum, which has basically flat response here. But from the spectrogram, I could guess, okay, since this is not actually changing by time, it probably does not carry any information, although it would, it still could, but well, this is just an example, simple example. And then I took a filter with Okay, let's see where do I have my let's see play frequency response. I took this filter. Sorry. And took this signal and after the system filter, I don't have any more that 100 hertz noise here, and I have actually this is preserving more or less the spectral properties of the passband, which was defined as a 25 hertz passband. Okay, so this was my show for today. Let me take a quick look at, yeah. So basically, on the third exercise, you would start from the similar picture as on the second one. There was the system you need to analyze by following the signal to find out which are the system parameters A and B, or B and A, actually. Maybe I should change those. System parameters B and A. And after that, when you have B and A, you can start playing with it. So you can make an impulse response of the system, define it as if infinite impulse response or FIR. As I said to you, this the flow chart does not guarantee anything. So even if there is a feedback, it's not a guarantee that the system is yet infinite impulse response. You must actually check it from the impulse response, the picture. Then using those B and A, plot the frequency response with a known sampling rate. See, we don't know the sampling rate until here, then it's set. And then does the system have linear or non-linear phase response? Okay, well, the phase response is non-linear. Well, that's non-linear. If you had a system which has a linear phase response, this is straight line. Like actually 4-point running average. So figure frequency response of the B is simply 1 times 4 ones and divided by 4. A is 1. And I have free sampling rate. So this would be the frequency response of a running average filter. Okay. And the linear phase response means linear. So that's linear. It's a straight line in phase response. And another straight line here. This jump doesn't mean anything as long as these are, it's just 180 degrees phase shift. So, linear or non-linear phase response, you can see it from the phase response graph. Then zero pole plot, plot the group delay. Okay, scale the system such that it has unit gain at passband. Yep, done. Then you will generate a sound sample. By the way, you need to practice a little bit more of this, how to calculate the correct signal to noise ratio when I give it as a dBs. Okay, reminder. So practically what you will be calculating is the from the standard deviation of signal divided by standard deviation of noise. Or that was all 10 variance of signal divided by variance of noise. In quite many cases, you didn't take into account the standard deviation of signal. Amplitude 0.4, sinusoid, then it's basically, when you don't take that into account, you make a quite big mistake there. So try to be more careful this time. So we'll take also into account that standard deviation of the signal when you are scaling. And actually, all of those who tested calculated the signal to noise ratio from the formula to test it before adjusting. All of those were correct. So test before submitting. Okay, so then make some signal with noise, calculate the spectrum of the last 4096 points. That should be quite simple. Spectrogram, and then filtering sound sample. So spectrogram is that nice color picture like that. And filter your sound sample with the system Q1 and calculate the spectrogram of the filtered data. Yeah. So basically you will see how that system filters this data here. Okay. Any questions? Okay, if there's no questions, then start working on the exercises. I will be online until 2 o'clock again. So, okay, have fun.